Hello everybody, I welcome you back in this course which is about linearization. In this video I will discuss with you two very important and illustrative examples where you can see how we can apply the Taylor series method in order to linearize a function and in order to solve then these linearized equilibrium points. So let me immediately start with my first example. So suppose we have a function which is non-linear and it's called the log function 1 plus x. And we want to linearize this function around a certain point, and let's call this reference point, the x0 point, 2. So first let me illustrate this function and then do the linearization by using or applying the Taylor rule. Well, if we want to plot this function, this is x, and here we would have f of x, which is the log. You can say this is f of x, which is the log of 1 plus x. Well, we know that the log function, in principle, not the 1 plus x function, so the log function has a 0 at point 1, it goes here to 0, and it more or less looks like this. So this is the log of x. But look, we have here the 1 plus x, so this is just a function that is shifted up 1 unit. So this would be the function log of 1 plus x, so the red one. That is the red one. And why? Because the log, the log at 1 is 0, but if we plug in here 0, then we have at x0, we have it here at 1. Okay, so we are approximating this function at my reference point x0, 2. So if we go up here, so this would be my reference point, and we are basically looking for the tangent, the linearized function at this point. So this is what we are looking for, question mark. This is my question mark I want to get in the end. Okay, how? Well, we all know in order to find this tangent line at 2, 0, we use the Taylor rule. Taylor rule or Taylor method. And we make a first order. Let's do first order, yeah? First order Taylor rule, not second order. First order Taylor rule. Okay, so let me repeat and recap. What is the first order Taylor rule? Well, we want to approximate a function f of x, which is nonlinear. And this can be done by taking the function at my reference point. Then we take the first derivative at my reference point times the difference my reference point plus higher order terms. But if we assume that these higher order terms are negligible, they're very small, then in approximation, my function f of x can be approximated by the right-hand side. Okay, if this is the case, let's do. Well, this function f of x is then the log function at my reference point, 1 plus x0, plus the derivative of this log function. Well, what is the derivative of the log function? Well, that is, of course, what you have learned already in high school, and I guess also in the first semester again. It's 1 over 1 plus x, here evaluated at x0, plus the inside derivative, which is, of course, 1 in this case, and then we have, of course, x minus x0. Well, this is simply, that is the Taylor rule. Yeah? Here we have used the Taylor rule for my function ln 1 plus x. That is it. And in the next step, of course, we can plug in x0, because x0 is also given, it's 2. So that's the log 1 plus 2 plus over 1 plus 2. I just make it really step by step. 1 x minus 2. Of course, that can be simplified. That's the log at 3. And then we have here 1 over 3 x minus 2. And that can be rewritten. Look, so that's a log at 3. and then we have minus 2 over 3, and we have plus 1 over 3x. And now look what we have here. So this is now my function f of x, which is now linearized. This is like a line, where this you can say is a horizontal intercept, my a. The 1 over 3 is my b, the slope, times x. This is a line. Yeah, can you see? This is simply a line where the a is a number. It's the intercept with yx. Yeah, basically this point here. Yeah, you can say this is log of 3 minus 2 over 3, yeah? And the slope of this line would be 1 over 3. Okay, that's it. So we have a log function in principle, the red curve, but now we have find around this point for x0 at 2 a line. And the line is this one here. That's a line. Okay, job done. That's it. That's the linear approximation of a log function around a point, and the point is here x0 defined at 2. Of course, you can do the linear approximation also at another point. Let's call it 4. Yeah. Then of course you would get a different line which has a different intercept, yeah, and a different slope. And you can do it for all the points you're interested in principle. You can play a little bit around, yeah, do it. That's always good to train it and to do it and use other functions. You can do it for exponential functions, for square functions, and so on and so forth. But that's the steps you have to do, and in the end you get a line, a linear function. Okay, so that's my example 1. Let's now do a second example, example 2. So suppose we have, as always in economics, so let's draw an example from macroeconomics. In macro, you know, we have not the price often here, we have the interest rate, the real interest rate. And as you know from my first macroeconomics class, we have a saving curve and investment curve, while investment curves are downward sloping and the saving curve is upward sloping. And the equilibrium point, of course, is the intersection. And you know from my discussion that all the equilibrium points above, it's called a current account surplus. And when we are below this equilibrium point, then we have a current account deficit. And that is in macroeconomics very important, and you probably remember that the current account is defined as export minus import, and from the income expenditure identity, Y is consumption plus investment plus government spending plus net exports or current account. We can rearrange it and we get saving minus investment is equal the current account. And so if the current account is positive, then we are in this territory. That means there are more savings, and you can see this saving is higher than investment because this is investment and this is saving, and you see here we have more savings than investment. That characterizes a current account surplus, and that's the case in Germany. Yeah, we export more than we import. Our current account is positive in Germany, and at the same time we have more savings than we invest. Yeah, that's the other side of a current account surplus. So now we want to calculate this, yeah, by using functions. So suppose my saving curve, which is the upward sloping curve, is a function 1 plus e to the power of r. Yeah, it's dependent on r. And my investment curve is also dependent on r, and it's downward sloping. I suppose here I used a nonlinear function in the graph, but to suppose it's given as a linear function, it's downward sloping, so slope is 1 over 2, so a half, minus x, and the intercept is 1. So it's basically, let's say I already linearized it by this red curve, yeah, to make the case a little bit easier. Okay, so the first question, let's call it Q1, calculate or compute equilibrium. Compute the equilibrium. Sorry. Let's erase it. Write it again. Compute equilibrium. Question mark. Okay, so what's equilibrium? Well, what you would do, you would simply equate, you would say, okay, let's say saving is equal the Westman function equilibrium. Then we write in the function that is 1 plus e to the power of r, and that is 11 minus 1 over 2x. Okay, then let's multiply it by 2, and let's multiply it by 2, then we have 2 e to the power of r, 22 minus x, and sorry, r, not x, that should be an r, here, r, okay, and now the next step we can simplify. For instance, we can bring the 2 on the other side, then this is 20, we bring the r here, then we would have 2 e to the power of r, e to the r plus r. Okay, so now find r. Find r. Yeah, that's the equilibrium interest rate we have to find. But look, that's not easy. Because we have e to the r plus r, and we have to solve now this equation for r. Then on the left hand side we have just r, and all other terms are on the right hand side. Well, that can't be done, actually, simply. Yeah, try it, but you will see it's not working, because there is e to the r, and we have plus r. Yeah, that cannot be solved simply for r. Okay, what is the way out? Well, there are two ways out, actually. One way is, let's call it case 1. Let's call it case 1. Well, case 1 is we use the Newton's method. Newton's method is helping us here to find this solution for this problem. And the second way is do linearization of my exponential function. That is what I will do in case 2. Let's first apply Newton's method. We also have studied in the previous video. Okay, so I can rewrite this as a following equation. 2 e to the r plus r minus 20 is equal 0. So this is now a function that is equal to 0, and we want to find for which r this holds. Yeah, for which r this holds. Well, in order to capture the same terminology, I can also write instead of r here x. Yeah, I can say, so let's relabel r by x. Yeah, r by x. Then we would have a function f of x, which is 2 e to the x plus x minus 20. And now we apply Newton's method. Do you remember Newton's formula? We want to find the k to the x of k plus 1, which is x at point k, minus the function of xk over the derivative of the function of xk. Well, that is xk. What is the function? Well, the function is 2 e to the xk plus xk minus 20. That's just the function, yeah, f of x. And now we have to find the derivative for the denominator. Well, that's also easy. Let's do the derivative of this function. Well, the derivative of the exponential, as you know, is the exponential. The derivative of x is 1, the derivative of a constant is 0. So that's just 2 to the exk plus 1. Okay, here it is. That is what you have to do, yeah, in order to find the solution, x the equilibrium, or here, as you see, my equilibrium interest rate. And how can you do this? Well, that's an iterative process. You take your calculator. Let's say you start with an xk of 1.5. Then you plug it in here, 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 here. You calculate the result, yeah, and you get a result. Let's say 2 point or 1.9999 or something like that. And then you take the 1.999, plug it in here, 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 here. Again, you calculate the next result. If you do this for 3 steps, this will approximate to an equilibrium point X or my equilibrium interest rate. This is an exercise you should do at home. That's homework. Yeah, just using your calculator, plugging in, starting with a number, calculating the x at k plus 1, then you plug in this new number again and do it for 3 or 4 or 5 times, and then you will see there will be almost no changes anymore after the comma, and that means it's stable. Okay, so this is one method, using Newton. There is another method, as I already mentioned, and that is the problem here. Actually, if we go back to this line here, the problem here is that on the right-hand side, my investment function is linear, no problem. But the problem is here that my saving function is non-linear. So let's do and linearize the saving function, and then let's equate again. Because then when we have it linearized, we have 2 linear functions that can be easily solved, of course. Okay, so that's my case 2. So case 2 of my example 2 is linearization of my saving function s of r 1 plus e to the r. Okay, how can we do that? Well, again, of course, and the point we try to linearize, I have to give, or you need some benchmark. Let's call, we choose an r or an x, 2. Yeah, that's my reference point, the x0, yeah, or the r0, you can say, is 2. Okay, rule Taylor. Here we apply the Taylor method or Taylor approximation method. Well, it's f from x. We do a first order, yeah, just first order approximation. First order approximation. Well, it's f from x. Then we take it at the reference point plus first derivative at the reference point, x minus x0. That would be the Taylor approach, right? Okay, let's plug in. It's my function 1 plus e at the reference point, r0. Then the derivative. What is the derivative of this function? So what is the derivative of this function? Well, the derivative of 1 would be 0, but e, the derivative in respect of r, is e to the r. Yeah, that remains. So it's just e to the r at my reference rate, 0, times r at r0, but what is r0? It's 2. Okay, so this can be rewritten. Look, for r0, I can immediately plug in here 2, that are numbers, and then we have here a number, and we can multiply the exponential inside the bracket. That gives me then here a 1 plus e to the 2 plus an r e to the 2 minus 2 e to the 2. So here I just have multiplied in the brackets, yeah, and then can be rewritten. So we have now linearized the function. Look, these are just numbers. That is somehow like the horizontal intercept. So this is 1 plus, and here we can factor out, oh well, this is even easier, this is just e to the square minus 2e to the square is just minus e to the square. That's just minus e to the square plus, that's the slope times r. Look, this is again like a line where this is my a, my intercept. The slope is e squared b times r. Yeah, or I came here from the Taylor rule, which is written in x, but here my x, of course, is r. So I should be better use here immediately the r, because here we have a function of r. And you see, it's a line now. It's a line. Okay, we got it. So now back to the problem. We want to know the equilibrium point. My saving function, that's now my saving function, but call it linearized saving function, therefore I make it tilde over s. My linearized saving function is 1 minus e squared plus e squared times r, and I equate this in order to find the equilibrium solution to my investment function. What is my investment? Do you remember? It was the 11, 1 over 2 r. 1 over 2 r. Okay, and now we have to solve it for r. Well, okay, that's possible. Let's multiply the whole guy with 2 first. Then we have 2 minus 2e squared plus 2e squared r, 22 minus r. Okay. Oh well. So can you read it? That is just a square. It's not looking like a square, so I have to make it precise. Okay, good. Now bring the 2 on the other side. Then we have 20. Then this 2e to the square also. Then we get a plus 2e squared. And I bring this r on this side and factor it out. Then I have here a 1. And here I would have a 2e squared. Okay. And now I can find my r equilibrium point, which is 20 plus 2e squared over this term here in the bracket, the parenthesis, 2e to the power squared. Well, if you calculate this, you would obtain an equilibrium point in your calculator. It's somehow 2.2 approximately. So now we have found from our graphical point of view, so if we go back for a moment, we have found this point 2.2. And now, of course, we are interested, what is my investment and what is my saving point here? Well, how can we do it? Well, we just use the investment function and plug in my equilibrium r we obtained. Well, that is 11 minus 1 over 2. And now my equilibrium point is this 2.2. And if you calculate this, then you would get, and that is equal to my saving in equilibrium, of course. You would obtain, if I did it correctly, something like 9.89. That means the interest rate is around 2.2 and the savings is around $10, or the investment is $10 or $10 billion, dependent on what the dimension is about. But in principle, what we obtained now the solution of my equilibrium point, this and this point. And you see there are 2 ways to repeat. One way is you equate it, and then you see, well, this cannot be easily solved for r. Then you have to use either the Newton's method, do this iteration, and then you would get a relatively precise r. Now that would be the somehow precise, but it takes this iterative way. Or you can immediately linearize this nonlinear curve by Taylor's method, and then do the equating it to the investment curve, solving it for r, and using this approximate solution in one of those functions, either the saving or investment function, in order to get then the saving and investment amount in equilibrium. The problem here, and that's the problem here, is when you do the Taylor method, you have to say, you have to do this linearization around a reference point. So you have to fix some reference point. And look, when you fix a reference point, I choose in my second case 2. Suppose 2 is here. Suppose this is 2. And if you now do the linearization here, well, you would say, well, this is, and the true equilibrium is from the black nonlinear curves. Well, then the red curve is relatively close to the equilibrium, the theoretically true equilibrium. You would say that this approximation is well done. But suppose you choose the linearization around a half, and a half is here. So if we do the linearization around a half, and the tangent line, it would be that point. And look here, the difference, the difference between the equilibrium and this line here is very large. This is the arrow term. It's the arrow. That would be not good. That would be not good. That would be a good linearization, because here the difference is very small, but here the difference is very large. So you see immediately the linearization has one risk. It is only precise and good if the reference point where you linearize is close to the true equilibrium point. And then the arrow is small. But if you linearize a nonlinear function around a point which is far away from equilibrium or our steady state, well, then you are very wrong with your calculations, of course. And so this is the critical point here is this, yeah? Choosing the correct linearization, the reference point where you linearize the nonlinear function, here the exponential function. Yeah? That's a problematic and tricky point, and therefore the Newton method, of course, would give you a clear evidence where the equilibrium point is lying. Okay, that concludes my two examples. I think now you should be ready to linearize functions and to calculate the steady state or the equilibrium point of supply and demand, or investment and saving curves, which are in economics non-linear in general. And then, of course, if you have these curves, you can also calculate the current account surplus, which would be the area above the equilibrium, by using a triangular formula for the area, or you can do also integration, of course, for a lower and a higher boundary, which should be given by the question or by the professor in order to do then the area calculus above equilibrium point for current account surplus or current account deficit below the equilibrium point. All right, okay. In the next video, I will now continue with this, and it's called log linearization around steady state, which is very influential in modern economics, in particular modern macroeconomics, when you go and study so-called dynamic stochastic general equilibrium models, DSGE models. They all do it by log linearization around steady state. Without that method, you cannot study and read current research papers. And therefore, I will continue in my next video with a theoretical introduction and some examples about the log linearization around steady state. See you. Bye-bye.